All right, so case one here, BESS Project Cost Evaluation. For the case description here, we're asked to provide an estimate for a BESS project that will be controlled by a utility as part of a tolling agreement with the following requirements. The required power capacity at the point of interconnect is 100 megawatts. The energy capacity, also dischargeable at the point of interconnect, is 400 megawatt hours, so 4-hour system. The cycling limit indicated from the utility is 1 cycle per day maximum, but of course, as you all know, in these type of tolling agreements that are common here in the US, they'll set a limit of 1 cycle per day, but that doesn't necessarily mean that they'll cycle it at exactly 1 cycle per day. Project lifetime for this case, 10 years. Location here, we're assuming New York, and deployment strategy, Overbuild. And the requirement for the technology to be used on the project is lithium iron phosphate batteries. Now we can begin with the design process here. So here, bring up Storlytics. So this is what you should see when you bring up Storlytics. So here, we'll just give a name for this project. Let's call it BESS Financial Evaluation. And the first thing we'll start off with is the general tab here. So first thing we'll do, as the slides show here, is specify the project life, 10 years. And by the way, for everyone in attendance here, you should see the slides within the chat. Jakir, are we able to share that, please?
Yeah, I'm pulling that.
All right, appreciate that. So in case I go too fast or you need to go back to something, the slides are there or will be there shortly. All right, so for this case, we specify the project life as described in the case description. Then deployment strategy here will specify user defined. We won't be doing augmentation just for this example. Auxiliary load source here, we'll do separate service. And to explain what this is, very commonly or somewhat commonly in BESS projects, auxiliary load will be sourced from a separate electrical service, not from the same point of interconnect. So in that case, you want to select a separate service for the auxiliary load source. But if your project doesn't have a separate service, then obviously your only option is to source auxiliary load from the same point of interconnect. And this project is transmission tied, so turn that on. Okay. And now we can move to the next step here, simulation options. So we'll turn on deduce financial results so that we can see the cost of the project and also revenue after we run the simulation. We'll also turn on the option to deduce battery degradation, which allows the simulation to calculate what the degradation will be each time step of the simulation based on how the battery system is being dispatched. For the initial state of health here, we won't make any changes. Its default is 100%, which assumes the battery cells are new. Some companies and users like to set this to 98% to account for some state of health loss during transportation or something like that, but really depends on your case here. But here we'll set it to 100%. And then finally here we'll turn on the option to reduce enclosure temperature regulation, auxiliary load calculation. And what this does is it allows the simulation to calculate what the auxiliary load will be, which is primarily in lithium battery cases, HVAC load to cool the cells when needed or to heat the cells. And if your project is in a cold environment, you'll need to heat the cells. So this option allows the simulation to do that automatically. All right, now that we're done with the general tab, we can shift on over to the interval data tab. But before we do that, let's go back to the slides here and check the case. In the case description, the cycling assumption is 1 cycle per day for the tolling agreement. That's the maximum the utility set. To simulate that, we'll use the standard cycle here. And we'll specify that the target POI power is 100 megawatts. Duration is 4 hours, as the case implied. And then we'll put 1 cycle per day. Right? Now, then we can go to meteorological profile. So here, for those of you not familiar with TMY3, these are typical meteorological year files. That's what the TMY stands for. And it's basically a CSV file that has ambient temperature data, irradiance data, and other data about the location. These file formats are available for free online from NREL and other sources. So you're not limited to just the list that's already here, which is primarily for the US. You can also find these files for, like I said, online for free for really most countries in the world. All right, in our case, this project is located in New York, so we'll just find the TMY3 file for New York and select that. And then we'll shift on over to the equipment section here. So here, let's go back here. So for the equipment, we'll select a battery model, which is generic LFP 306 amp hour cell. Here, I'll go ahead and select that. And then SMA for the inverter, we're using an SMA Sunny Central Storage 3950 up. Some of you may be familiar with this inverter model. We've used it on multiple projects. Okay, and then finally, for the enclosure, we'll use generic enclosure air LFP. Okay. Perfect. And for those of you not familiar with our enclosure models, the enclosure model basically controls how much auxiliary load is being consumed by the battery system. It makes a big difference if your enclosure is made out of steel or if it's made out of concrete or any other material. It also makes a big difference whether your enclosure is air cooled or liquid cooled. So if you open up the enclosure model, you'll find kind of all these specifications and the auxiliary load model here. You don't have to be super familiar with all these parameters to run a simulation. All right, so now we selected the models here, and you'll notice that the auto size project button came up. And just to take a step back here, so when you're trying to deduce what is going to be the cost of a battery system, your biggest unknown is the degradation that's going to happen to the cells, right? Because based on the amount of degradation that's going to happen, the cost of the system changes, because if you're going to get high degradation, you're going to need a bigger battery up front, or you're going to need more augmentations, and batteries are not cheap, they're expensive. Not knowing degradation really prevents you from being able to estimate what a project cost is going to be. All right, so that's why with the auto sizing tool here, once you specify the conditions here that under the general tab, and specify how the system is dispatched and where it's located and the equipment you're using, then the system could be sized. Now, when you click auto size here, you'll see this window pop up. It'll show you basically a summary of the inputs you have. So we are designing for a 100 megawatt project, 400 megawatt hours. We're turning on degradation, obviously, because we want an accurate representation of the estimated cost of the project. So we have to account for degradation. Initial state of health, we're assuming 100% state of health in the beginning. And also, for those of you that may not be familiar with what state of health is the percentage of energy that the battery can withhold compared to that energy when it was new, basically. So if a state of health of 50% just means your battery can only hold 50% of the energy it could hold when it was new. Overbuild basis here, it's user defined, like we said. Overbuild years, 10 years, because the project life we're assuming here is 10 years, and we're not doing any augmentations. Okay, all right, let's go back to auto size. So we went over these items here. We can then click OK. Then it'll tell us, all right, are you sure you want to kind of auto size with degradation? This may take a little bit of time. So here we'll click yes. And what it's doing is it's running multiple simulations on the back end, trying out different project sizing, going from small energy capacity to larger. And every time it does that, it simulates the project and finds the degradation, and is trying to make sure that your target power and energy at the point of interconnect is always being met. All right, so auto sizing has completed here, and you'll notice that all the parameters in the other tabs have been filled out. Under system specs here, the number of modules per rack has automatically been set to 8 modules per rack. So here, these have been set to 8. The number of racks per inverter to 42, and number of inverters for the project has been set to 30. You'll also see that the losses have been specified. For transformer copper losses, the default assumption is 1%. For core losses, 0.1%, and here we're assuming 0 auxiliary load losses. And when I say auxiliary load losses, this is the constant component of the auxiliary load losses, which does not include the HVAC. So here, if you read the hover message here, it's control devices and excludes enclosure and HVAC load. Operation. Maximum state of charge has been automatically set to 95%, minimum state of charge to 5%, and the initial state of charge for this simulation is 10%. Okay, now we can shift on over to the financial tab, which is the main reason why the run button is not enabled here, because the contract term for the tolling agreement here is needed to be input. So we know the project life is 10 years, so we can just put 10 here. We'll see that the run button here has come on. Right.
Thank you.
So here, let's just go to the Sankey diagram, right? So here, this is basically a summary of all the losses in the system. Throughout the simulation, about 146 megawatt hours were charged at the point of interconnect. 1.16% of that was lost within the generation step-up transformer. And then you can see these percentages here, 0 for the secondary GSU system. So on the other side of the GSU, basically, that's 0. And then within the PCS, you have 1.24% losses. Inverter charge here, 1.58% losses within the inverter. Within the battery, you can see that within the internal resistance, the series resistance here, 1.61%, 0.02% self-discharge, because here we have a lithium model, and lithium has somewhat low, very low self-discharge if you compare it to nickel hydrogen or zinc batteries. Finding open circuit voltage hysteresis data. And then, so this is all while the system was charging, and you have the same values while the system was also discharging. Okay, and back to this point here, the reason these are all zeros is because if we go back to our simulation here, auxiliary load is being fed from a separate source, not from the point of interconnect. That's why there's no kind of, it's all zeros here. If we had it as auxiliary load to be fed from the point of interconnect, you would see the values here. Okay, so let's come back here, standard cycle, and the simulation again. And we were going over the report. All right, so now when I clicked generate report, this report came up. Of course, we just went over the losses section, but since this case study is about the financial results, I'll just fast forward to that section. And then if there's any questions, we can go back to any of these sections here. All right. This is the financial section. Everything is laid out in a table format to begin with. I won't go over line by line here, but I'll just jump on over to the figure. So here you have a net present value chart. So it's telling you what's the overall cost of the DC block in this case, based on how much degradation was calculated and the resulting beginning of life capacity. So if we go to this chart here, you can see that the beginning of life capacity we have is about 557 megawatt hours were needed for the project to be able to last for 10 years and maintain that energy, that 400 megawatt hour target energy capacity at the point of interconnect. And that ended up costing a little over for the DC block. Let's see here. Right, about $90 million. Then you can see the PCS cost portion, GSU, high voltage breaker, and then depending on how kind of detailed you were with your financial model and what kind of cost components you want to include. So here I'll just include all these and run another one. But the more kind of parameters you add in here, the more detailed the financial results are going to be here. I think I should have actually had them on in the first one here, in the first simulation. All right, I can probably pull up another report here. There we go. All right, so here, right, for annual Opex breakdown, you'll see the energy loss cost over the project lifetime here in light blue, and then the state of health guarantee cost in dark blue. Of course, the state of health guarantee is not there for the first 3 years because the standard warranty assumption on the battery is 3 years, but all of these parameters you can edit within the financial model, which is this one. The good thing about this is since it has a model format, you just need to edit it once based on your case and save it, and then you can use that with all your kind of project simulations. So under cost here, you have the equipment cost section, which includes the battery, the PCS, the GSU, and high voltage breakers. Opex costs, so standard warranty, so we have that as 3. That's why you didn't see any state of health guarantee costs for the first 3 years. State of health cost at year 0. State of health cost change rate, if any. Auxiliary load, energy cost, losses. And even though it's not relevant for this simulation, but for augmentation cycles, if there are any fixed amounts per phase for each augmentation, which there obviously is, so you want to have that filled out. Augmentation phase change rate, auxiliary or augmentation energy dependent cost, and also here balance of plant. And Jakir will get into the details of these parameters in the next case study here. All right, so here, then we can go to the revenue side of the equation. So since this is a tolling agreement, you can see fixed revenue over 10 years. Of course, if we had it set as a merchant market, you'd be seeing variable kind of revenue depending on what the battery is doing based on the simulation. Here it's a tolling agreement, so it's a fixed revenue. Also, we didn't assume any liquidated damages for RTE, for availability, just for the sake of simplicity here, but we can turn these on in a real project kind of evaluation. You would definitely want to have these parameters on to account for any LDs you may be paying based on underperformance. And then here, the overall cash flow, so how much you're spending in the beginning of life of the project, and also the revenue throughout here. Now, because this is a overbuild, so the IRR doesn't look as attractive as probably you would get on a lot of projects when you augment, but this is just obviously for the purpose of demonstration. Right? And then here, discounted cumulative cash flow showing break even at year 10. So not so good. Obviously, this is an overbuild project. All right, coming back here, let's go to the slides here. And the slides here are very detailed, and we obviously sent them through the chat. So for those of you who may have missed anything, you can go back to them. Right, so we covered the degradation, the costs here, the revenue, right? Now, observations here. So we're able to deduce the preliminary financial estimate for this project right now within 44 minutes, not 30 minutes as the slide's saying. We've been able to do that in less than 30 minutes previously, but all right, second one here. Something you may have noticed is we did not need to input any assumption on degradation rate. We just described how the system is being dispatched, selected the models that are planned to be used in the project, and degradation was automatically calculated because, like I said, it does make a huge difference how much degradation per year is happening as it relates to the beginning of life capacity of the system you'll need, which heavily affects your capital cost and also augmentation costs. Right, inverter capacity was automatically oversized to meet reactive power requirements. So our project actually needed just 100 megawatts at the point of interconnect. You'll see here that our total inverter capacity is 118 megawatts or MVA. And this is mainly to account for the reactive power that's being consumed within the transformers here between the inverter and the point of interconnect. Obviously, if we increased the or decreased the power factor requirement at the point of interconnect, in other words, if more reactive power was needed at the point of interconnect and we're not at unity power factor anymore, you would see this number go up when we auto size. So after we do the auto sizing, you'd find that you'd need more inverter capacity to just inject reactive power into the grid. But that's, you don't have to guess about that. Once you just click that auto size button, it'll automatically be deduced based on kind of the simulation. All right, then finally here, since I alluded to this one, since we're overbuilding for 10 years, project IRR is not that attractive. So more than 50, you can notice that more than 50% of project net present value is for the DC block. So that's why. Right, so now what? If this were a real project, the next thing you would do here in this case is you obviously want to improve your project economics. You don't want to break even after 10 years. You want to break even probably about, a very good project would be like 3 years, 4 years or so. So you try different technologies. Something that will be very effective is running the augmentation optimizer to optimize when you actually do an augmentation. And that kind of, we've seen in some cases, will reduce kind of net present value cost at about 15% in some cases. So very impactful and does not affect the performance of the project in terms of kind of the functions it is performing. Second thing here, optimizing battery selection. So we can Now go back here and see, all right, we tried it using, in this case, we did a generic battery, but if this were a real project, you'd want to use any of these OEM models. And then if you're finding that it's not performing well, you can try others until you get performance that is heavily suits your project requirements or is more kind of financially advantageous. And finally here, so if everything looks good and we're satisfied with the system design, then we can generate a one-line diagram for the system that's been designed in preparation for any IR applications or any kind of next steps for the development of the project.